guess we can go ahead and get. Did you get a chance to watch the video that I suggested you guys watch before coming?
Yes, I kind of skipped over some of the just doing the pure math
Yeah,
to focus on the theory part, but yes, I did get to watch it.
that's cool. That's the main thing that I wanted to make sure y'all had covered because I actually worked all the examples from the book, well, equivalent examples to what's in the book in there. So you've got the whole time covered. So this is just more or less a Q&A for you guys. And then I'm starting into chapter 19. I want to give them a few more minutes before I start into 19, but that's what we're going to do. And you might be the only one here. Who knows? Of course, it's not like I've never taught class when no one's
I'm
here.
betting that I'm betting that a lot of people show up for the regular nighttime 242 because it's later, it's convenient.
Yeah, I forgot about that. So yeah, that could
If they're
definitely
going to be, the problem is again, it's in the middle of my chemistry.
be
It's in the middle of my lab section.
Gotcha. Well, I think I will do that. I think I'm just going to jump right into 19 since you were good enough to have watched that already. Did you have any questions about any of those examples I worked or anything you didn't understand?
No,
Like it's a
because it's
pretty
all
neat
stuff
thing
I've
that you've done before.
yeah, I mean it's stuff I either did in high school way back when, like because a lot of that's just division. So we
Right.
did a lot of those like a lot of the like I knew about the meteorological stuff already.
Okay. So you already did,
And
relative humidity and have you
yeah.
have you found the elevation of a boiling point?
Yep, that's an entire section in Chem 112.
Gotcha. Cool.
So anyone who's done Chem 112 spent
Should have done that
probably a
already.
week or two on that. So
That helps me. I wasn't sure. They didn't cover that in my chemistry class. At least I don't remember it. But hell, that was, a long time ago. That was like 1989,
okay,
90. So yeah.
it's a difference between TCC's anyone who's a biology or chemistry major had to take Chem 112 in
Hmm.
order to take organic, and whereas your engineering majors only have to take Chem 111.
Gotcha.
And it's in 112. So I would not be surprised if other people haven't done it, but I have.
Gotcha. Well, I did go ahead and set the due dates later back just to make sure everybody had ample time to do their homeworks. Hopefully you were able to see that.
I have not started it yet.
Okay.
I kind of address my homework in the order that it's due,
Yeah.
unless it's something huge. So,
Gotcha. No problem. Well, I guess I've waited long enough. I'll go ahead and get started. So, what we're doing here is chapter 19, and chapter 19 is about the first law of thermodynamics. In fact, it's called uh, the heat in the first law of thermodynamics. In order for us to understand that, and this because you have had chemistry is something but we're going to have a oddity in that you're not going to be used to this, but we have a slightly different sign convention we use in physics than you use in chemistry. So you've probably already had the first law of thermodynamics, and in the first law of thermodynamics in chemistry, they normally say something along the lines of delta E, the internal energy, or delta U, the internal energy, is equal to Q uh, plus W or minus W. We use one version and chemistry uses the other one. We specifically, where'd it go? We specifically talk about the work done by the system. So it's Q minus W, whereas in chemistry you talk about work done on the system. So for you guys, it's Q plus W. That's the main difference that you got to realize. Other than that, it's no big deal. So I'll start off by explaining exactly what heat is. Now, originally, they had this idea that heat was something that was contained inside of an object and that it was actually a fluid. They treated it like a fluid and they named the fluid the caloric, which is where we got the origins of the word calorie. But they said it
really
was
quick
the,
question.
yes,
Can you just go back really, really quick? Minus W is by the system, plus W is on the system.
yes. Minus W is done by the system and plus W is done on the system.
Okay, sorry, that is a really important note that I need to put in my notes.
Yeah,
So,
yeah, I would agree. Basically, physicists at this time were studying steam engines, and that's why we were trying to make sense of that. And all we cared about was how much work output it was, so we could calculate efficiency and that sort of stuff. So we geared everything as if work was the work being done by the engine because that was the important quantity. Therefore, if you're thinking about the heat inside of a system, heat added to it is going to increase that. So you have delta E equals the heat Q, but heat work done by the system takes energy away from the system. So you have to subtract that W out. So that's why it's delta E equals Q minus W. And in your case, they weren't focusing on steam engines necessarily. So they were more focused on the work done by the environment on the chemical that they were studying. Hopefully that makes it easier to remember as opposed to just even more confusing.
Oh yeah, it's not that hard. I just need it written down because I'm going to need to review it.
Gotcha. So we use the word heat in everyday life in a lot of different ways, but to be honest with you, in physics, as in all sciences, we have to have very precise definitions of everything we're using so that we don't disagree from one scientist to the next what the definition of a certain quantity is. So heat is really the transfer of energy from one object to another, and it's basically due to a temperature difference. So, for instance, if you put a warm body, let's say a Rubik's cube that was sitting in a, because I have two Rubik's cubes in front of me. So, if you have a Rubik's cube that's been sitting in a sauna and is at a 95 Celsius degree, or let's say 95 degrees Fahrenheit, and then you put it next to another one that was only at 60 degrees Fahrenheit, then the 90-degree one will actually start heating up the 20-degree one or 60-degree one because of this thermal contact to them to each other. So what's going on there is heat is flowing from the hot object through their point of contact into the cold object, and that is called conduction. Heat by touching is conduction. We'll learn later that there's also heat by radiation. That's how the sun gets its energy to us. We didn't realize at the time when we first started dealing with these things in the 1800s and even before, we didn't realize that waves could travel without a medium. So we just assumed there had to be some medium out in space that allowed the waves of radiation from our sun to reach our Earth, and in that for that we actually named something called the ether. Well, when we did an experiment called the Michelson-Morley experiment to detect how fast the Earth moved and in what direction it moved relative to this ether, we kept getting null results. So a guy by the name of Lorentz came up with an ingenious mathematical way he could make the experiment makes sense in a world where there was ether. And what he imagined was that the ether was sort of compressed along the direction of travel and all this stuff. And he got these really weird equations that, oddly enough, became exactly the right equations for relativity. But that was because he was making up an ad hoc solution to why the ether didn't appear to move relative to the Earth. And Einstein later says, well, for starters, there's no such thing as ether by the time he got there. But Einstein figures out that if you assume the speed of light is a constant, independent of the motion of the source and independent of the motion of the observer, then you get the exact same equations that Lorentz had derived for the ether, and they're called the Lorentz transformations. And that is the case where Lorentz did something for all the wrong reasons, got it wrong, but turned out to be exactly the right equations that Einstein was able to later derive as a result of assuming that the speed of light is a constant. Uh, so that's some of the background of what we're going through. But the main thing is in outer space, they didn't think there was an ether. They thought there was an ether because they had to have some way for waves to travel. When they did an experiment to detect the ether, they got a null result, which suggested there was no ether. And they tried to fix it with the Lorentz equations. And the Lorentz equations later became valuable for relativity in their own right. Even though Lorentz derived them first, he did so sort of like a monkey with a typewriter or something like that, doling out a sonic. But it wasn't, it was, and I shouldn't say that disparagingly because it's not an insignificant amount of work to figure out those formulas to correct for the ether drift or whatever. So it's still a big deal. That being said, Again, we're dealing with old theories where we thought of heat as a liquid and it flowed and so on and so forth. But generally, heat is energy in motion. It's energy being transferred. It's also, in some sense, something that you can sort of imagine as a bastardized version of energy. Because, for instance, if I throw a ball up or a pin up, then I'm taking the energy that I give it from my, ATP and all the stuff in my body that makes my muscles twitch and all that. They're actually being applied to muscles, causing a force to be acting on the pin or whatever I'm throwing up. Then once that pin leaves my hand, it has basically just kinetic energy and potential energy associated with it. But as it goes up, 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 the kinetic energy is decreasing, decreasing, decreasing. Then it gets to its max height, at which time now the kinetic energy is a zero, but the potential energy is a maximum. And then it starts to fall back down such that the potential energy is dropping again and the kinetic energy is increasing in exactly the same way so that the net energy in total is always the same. So that's the way mechanical energy behaves, and it's not uncommon for us to get very close to 100% of the kinetic energy back after we threw it up and it became potential energy. Well, heat isn't like that. Heat is a bastardized form of energy that can be basically cannot be completely conserved. So once you actually convert energy into heat, some fraction of it's going to be lost. And it's important that we understand that, especially once we go into the discussion of heat engines, which is what we're going to discuss in chapter two. So I just want to keep that in mind. We went
Chapter
ahead,
2?
excuse me, chapter 20.
Okay. I'm sorry.
22, they're the same thing, right? They both start with the number two. So, the calorie, your book says, is defined as the amount of heat necessary to raise the temperature of 1 gram of water
I will be
by one
honest,
Celsius
you can
degree.
skip this bit because I literally had this in cell biology
Gotcha.
literally yesterday. Like, literally, I was taking those notes yesterday, so you can skip that part.
Well, I can't because I still got to let the other students know that didn't show up in case they come
Oh,
back and watch this.
yeah,
But
true.
and specifically, they defined it because they knew it might be different for different ranges of temperatures. But specifically, the calorie was designed to be the amount of heat required to raise 1 gram of water 1 Celsius degree from 14.5 to 15.5 degrees Celsius. It turns out also the kilocalorie was designed to be basically the amount of heat required to raise 1 kilogram of water by 1 Celsius degree, again between 14.5 and 15.5 degrees Celsius. Another unit of energy that is used in the British system was based on the same thing with water, but of course in that system they'd use 1 degree Fahrenheit, so it comes out a little different. They have, as well as this, they have the joule, which is a unit of energy that we have already used in 241. We're going to use it predominantly in this class as well, but the calories used and the kilocalories is well used as well. I should also point out that the calories that you're used to on the back of food wrappers, that's the kilocalorie. And of course, I know you know that because in chemistry, I'm sure that they talk about that a lot. But the main thing is that's a thousand calories, not a regular calorie. So if you go and calculate the mechanical energy that you expended in climbing up some height, on a stair climber or actual flights of stairs, you got to remember that calorie is going to come out in calories. And then when you compare that to how much of that you have to do to make up for some cheesecake you ate, then you're going to have to multiply the calorie that you have in your cheesecake by 1,000 to make it match the calories that you calculated from your change in potential energy. Another unit of energy is the BTU, and another one they use in gas companies is called the therm. So British thermal unit, joule, calorie, kilocalorie, and therm are all different energies used. Heat is not, I repeat, heat is not a fluid. So I just want you guys to know that, and we're going to go from there. Now,
Is that a common misconception?
I don't think it is now, but it's easy to fall into that. Like if you're just being sort of rogue and learning science on your own without a science class, It's very easy if you happen to have thought of that once to think that might be how it is. But if you've been reading the books, then no, you're not going to make that conclusion. So I don't think it's that prominent, but it might be from people that are self-taught. So the first thing I want to talk about is the mechanical equivalent of heat, because this is a really big deal. In my chemistry class, which was the first real science I took, I never took a physics class before I took my chemistry class. I took chemistry class in high school. I actually ended up failing it because I was such an awesome student and didn't really partake of homework and stuff of that sort. But then I got to college, and the first science class I took was chemistry again, and then later I took physics. But I remember them talking about this, and I used it over and over again, and I didn't really get it so much. So I want to explain to you guys. This is the mechanical equivalent of heat. So James Prescott Joule and his family, by the way, they might have pronounced their name more like Jowls, Joule, is the way you pronounce is the way you spell it. But there's a beer in Great Britain called Jowls, and that's from their family. One of the things the Joule family did was made beer, but they also made cannons and did all sorts of work in basically the beginnings of engineering of thermodynamics. So they were the ones that could drill out actual cannons and see how much heat was gained and all this stuff. So they had a lot of works they were doing with regards to their own way of living in terms of the way they were making a living. And because of that, they were predisposed to making discoveries. And what they tried to do was figure out if there was a mechanical equivalent to heat, because heat was something they measured with calories because it was defined as the amount of energy required to bring 1 gram of water up 1 Celsius degree from 14.5 to 15.5 Celsius degrees. But in this case, they wanted to know how was that related to the joule, which is what everybody was using to calculate potential energy, kinetic energy, stuff of that sort. So their experiment looked something like this. I'm going to go ahead and share my screen with you guys now. You guys, plural, like there's more than just you here, Shannon.
You're also
I
talking to my cat.
Oh, gotcha, gotcha. Well, I want to keep the cat informed. Nothing worse than a cat that don't know physics. Okay, it looks like it's coming up now. All right, so the experiment that Joule designed, you can sort of look at like this. Let's imagine we have a beaker of water like this, and let's imagine we've set up a little propeller in there connected to an axle, and the axle runs up out of the water and is mounted so that it can freely rotate in a circle as a result of the string that runs over a pulley. And from that pulley, we have the string and a mass M hanging. And this mass M can be dropped a distance h and therefore accumulate amount of energy equivalent to M times G times 8, which is the potential energy. Now, in addition to having this in here, they had a thermometer as well. And what their plan was we're going to go ahead and imagine uh, taking this propeller and stirring the water to some extent. And in so doing, we expect that the uh, water is actually going to get a little higher in temperature. In other words, they thought as a result of the random motions of the molecules, which you've already learned about, is representative of the temperature. They didn't necessarily know all that at this time, but they had some sense that it might be related. And what they thought was if you had a little propeller hitting these molecules and speeding them up, eventually all the molecules would speed up and have an average net speed that's a little higher. And that little higher ultimately in modern day physics means it's a higher temperature. So when they did that, they ended up setting mgh equal to the equation for the changing of temperatures. And the changing of temperature was, for instance, the mass of water, big M, times the specific heat, which was C, times the change in temperature, delta T. So they could calculate the energy on the left in joules, and then they could calculate the energy on the right in calories, And from doing that, they could then, assuming their experiment was well designed and didn't have a lot of random errors in it, then they could make an equivalent statement between the calorie and the joule. What it turned out to be was that 1 calorie, that's a lowercase c, 1 calorie is equal to 4.186 joules, and similarly, 1 kcal, which equals 1 calorie, is equal to 4.1, oops, missed a letter, missed a number there, 4.186 kilojoules. So yes, that is a conversion factor that allows you to convert back and forth between joules and calories and between kilojoules and kilocalories, but it is a fundamental difference thing. It's a discovery that this heat that they thought was a fluid that flowed from one object to another, and was entirely different from mechanical energy. And this other quantity, mechanical energy, which could be potential energy, kinetic energy, that kind of stuff, were totally in different and unrelated quantities to some extent. But by doing this, they showed that in fact they were related. And therefore, this mechanical equivalent of heat is not just a conversion factor, but a fundamental change in understanding of heat and energy. Does that make sense?
Yep. I just so you know, my microphone is actually muted from a button on my microphone, so it takes me a second.
Gotcha, no problem. So I'm going to go ahead and work the equivalent of example 19.1, and let me read that off. It says, suppose you throw caution to the wind and eat 500 calories of ice cream and cake. So I'm going to say Q is one of the forms of heat. Q is the symbol we use for heat, by the way. Q from this cake is 500 calories, and I wrote that with a capital C on purpose. Okay, so suppose you throw caution to the wind and eat 500 calories of ice cream and cake. To compensate, you want to do an equivalent amount of work climbing stairs or a mountain. How much total height must you climb? So height is equal to question mark, and we're going on the assumption that your mass times g times h is going to be equal to q, which is m times c times delta t. So what we're saying here is the heat required to change an object's temperature from T0 to some final temperature T, okay, that is directly proportional to the mass of the substance whose temperature you're changing, because it makes sense that a drop would take less energy to warm up than a gallon of a liquid. You would also think it's directly proportional to the change in temperature. So, for instance, a change in temperature from 50 degrees Celsius to 51 is a lot different than a change of 50 degrees Celsius to 500 degrees Celsius. So, again, Q is proportional to delta T. You could also take into account what the material is made of, and that would be yet another constant. And then you could put another constant in between the proportional symbol and the Q, and to replace the equals. Okay, so that's what we normally do, but this is another case where we decided not to put an extra constant K. We just assigned the constant C, which we call the specific heat. We assign that to the material, and that takes it. So now we have an equation, Q equals MC delta T, as an expression we should know. And this C here is called the specific heat. And as you can tell, it must have units of joules or calories per kilogram or gram per Celsius degree, or maybe even Fahrenheit degree. Okay. So if I set these two equal to each other, I have to say, okay, well, Q is equal to MC delta T, and we also have MGH. So I'm going to go ahead and calculate Q. Q is 500 calories, which equals 5.00 times 10 to the fifth lowercase calories. And then we're going to use a conversion factor that one lowercase calorie is equal to 4.186 joules. Got a problem with writing that one today for some reason. 4.186 joules. So I'm using mechanical equivalent of heat to find out how much heat this is in joules as opposed to in calories. So in doing that, I'm saying 5 times 10 to the fifth times 4.186 gives me 2.09 times 10 to the 1, 2, 3, 4, 5, 6 times 10 to the 6 joules. Now I'm going to assume the average person might weigh, let's say, 60 kilograms. Okay, I'm not the average person. I'm closer to the big 110 kilograms or something like that. But the average person might have a mass of 60 kilograms. Therefore, mgh equals 2.09 times 10 to the 6 joules means that we're going to have h is equal to 2.09 times 10 to the 6 joules divided by 60 kilograms times 9.80 meters per second every second. Now notice a joule is a Newton meter, and 1 Newton is equal to a kilogram meter per second squared. So basically, the joule in the numerator is kilograms meters squared per second squared. And you can see that the kilogram, the meter, and the second squared is all going to cancel out, and you're just left with a meter. So I'm going to take and divide this by 60 times 9.8, close parentheses. That gives me 3.56 times 10 to the third meters. So the height you'd have to climb is roughly 3,600 meters, which is on the order of 11, 12,000 feet. So that's quite a bit. But luckily, you really don't have to do that. It turns out your body is on the order of like 20% efficient, not so great. So if you wanted to figure out what that would be, we could say this is approximately 3.56 times 10 to the third meters. We could really say, well, since we're only going to get about 2% of our calories that are just pure energy that aren't wasted in the friction and energy loss due to muscles and all that good stuff, then we could make it as close to maybe 700. So the answer is roughly 3,600, but body only about 0.20 efficient. So 80% of the heat that would go into climbing that height is just going to be wasted. And therefore, you can sort of think of it as the equivalent. Since we're going to waste so much in getting on there, we only have to go 20% as high. So that would mean 20% of 3,600 meters is 360 times 2, which is about 720 meters. Any questions on that?
No, it's pretty straightforward.
Yeah, yeah. The biggest thing is trying to figure out how to make use of that percentage. There's a lot of different ways to do it. And we're going to learn about efficiency later, but right now, I just wanted to make sure you knew that. Yeah, it sounds like you can't get anything done with exercising to get rid of calories. You can, but even when you do, it's still a pretty monumental task. If you're trying to, ward off the calories or wear off the calories that you got from, something that was 12 or 1300 calories, uh, that's not really going to happen too easily, even though our body's only 20% efficient. So, what we need to talk
And
about, go
just
ahead.
one small thing, I'm very sorry if you hear my neighbor's dog barking. She's a Great Pyrenees. She never shuts up.
Okay, no problem. I hadn't
And
heard it
she's
yet.
she's going like crazy and it's really close to my office. I'm really sorry if that happens.
Okay, no problem. I've got the TV on here where me and the dogs are watching Nick Jr. So I see fish swimming across and they're going, outside, outside, everybody outside, outside, outside. So I don't know. I expected to hear some of that in some of these videos too. Uh, we're
Not
going
Blue's
on to,
Clues?
I can't remember the name of the show. It's not Blue's Clues. I don't know what it is. It might be. Maybe it is Blue. I think Blue's Clues was that little blue dog, wasn't it? All right, we're
There's now
going on.
another blue dog, believe it or not.
Oh, okay. Well, we're going on to internal energy, and the sum of all the energy of all the molecules in an object is called its internal energy. This is another chapter, and in fact, 17, 18, 19, and 20 are what we call thermodynamics chapters, and a huge fraction of learning thermodynamics is just learning a lot of terminology. Things like quasi-static and static and internal energy, thermal energy, uh, adiabatic, isochoric, isovolumetric, can't remember another one, but anyways, there's just a lot of bold face terms in chapters 17 through 20. So as we're covering them, our first test, for instance, is only going to be on 17 and 18, which is due February 1st or 2nd. You can check on Canvas to be sure it's already marked there. But the next test after that would be including chapter 19. So when you're studying for chapter 7 and 18, make sure you write down the definition of everything in bold print and do the same thing with chapters 19, 20, and all the subsequent chapters. I rarely see a bold-faced term in your book that I don't consider important enough to ask you about. One exception, for instance, would have been in chapter 18, the word diffusion. I wouldn't necessarily ask you because we skipped that section. So, like I said, the internal energy is the sum of all the energy of all the molecules in the object. Now, that means the kinetic energy of translation, which we've already learned, moving left and right, the whole molecule or atom moving left and right is one of the components of the velocity, the translational velocity. Then moving up and down is another component, and then moving in and out is the third component. That's Vx, Vy, and Vz. There's a kinetic energy associated with that translational motion, but there's also kinetic energy associated with the molecule spinning about this axis are about this axis. That's another kinetic energy. In principle, it could be about this axis, but that's just individual molecules like on the end of a spring. So it turns out to be not a significant amount of energy. But that's some more kinetic energy. And then in addition to that, you have the potential energy, which is in equilibrium off and on with the kinetic energy of the masses actually vibrating back and forth. That's another type of energy. Only those three translational kinetic energies are related to temperature. All those other velocities and kinetic energies are associated with the internal energy of the substance or the object, but have no effect on the temperature. So, in order to distinguish between temperature, heat, and internal energy, I want to remind you guys that temperature is the average random kinetic energy. It's directly proportional to the average random kinetic energy of translational motion of the atoms slash molecules in the substance. Heat is energy in motion. Heat is a transfer of energy from one object to another as a result of a difference in temperature. So, for instance, when I take and rub my hand back and forth on my desktop, I can feel my hand and I can feel the desktop both getting warm. That warmth has been a result of me applying energy to the desktop as well as to my hand. And then when one gets hotter than the other, heat will flow as a result of that difference in temperature from the hot object to the cold object. That's going to turn out to be a version of the second law of thermodynamics, which is extremely important. Okay, it's even though we normally skip chapter 20, I still cover it rather lightly, but quickly, just because I want you to know the second law of thermodynamics. But the first law of thermodynamics is basically a conservation of energy. The second law of thermodynamics tells us which way things happen. So, for instance, it's perfectly reasonable for a coffee cup to be sitting on a table. You accidentally knock it over, it falls over off the tabletop. Coffee starts to spill out and go everywhere. It hits the floor, bounces and shatters into bunches and bunches of pieces, and the rest of the coffee goes everywhere and stuff like that. That happens all the time. That also doesn't violate conservation of energy or the second law of thermodynamics. But here's the neat thing: you can imagine all of that coffee jumping up out of the carpet, landing in the cup that was in the process of shattering, and then all the little individual pieces of the shattered cup jumping back together to form the cup, and then the rest of the coffee filling up the cup and jumping back up onto the table. And then at the end, we'd have a full cup of coffee being held together just by, the friction that the pieces had. There's nothing that violates the first law of thermodynamics for that happening, for the coffee cup to jump together and jump back up on the table. That's not violated by the first law of thermodynamics, but it is violated by the second law of thermodynamics. So I want to keep that in mind for you guys when we do chapter 20. Uh, so that gives you a good difference between temperature and heat, and also tells you the difference between first and second law of thermodynamics. And then there's a third quantity, the internal energy, which I just told you about, and that's the total energy inside the object that you're studying or the substance that you're studying. And it's important that we remember that heat flows on its own from a hot object to a cold object as a result of the temperature change. If they're actually touching, it's done by convection. If the two objects might be separated by some third medium, like a hot object dropped in the bottom of an aquarium, obviously the hot object heats up the water around it. That water then expands, and because it's expanding, it's lower density, so it floats up to the top. But now it's water that's heated that at a higher temperature, and it's floating up to the top. That hotter temperature water could actually heat the air above it. That could be the thing that's actually receiving the heat via convection, is the actual atmosphere above it. And then after it dumps off that energy to the atmosphere above it, it's now back pretty close to the same temperature it had, so its density is high enough that it sinks back down, and some other water that's been heated pops back up and does the same thing. That's convection. That circulation going on, that's convection. And then the third way, like I said, was radiation. That doesn't require any touching. That's just a matter of a wave traveling over space and delivering the heat via that wave. You can imagine the waves, just like ocean waves make, boats float up and down. Well, waves of electric and magnetic fields can actually arrive at us and cause our electrons to move up and down and all sorts of crazy stuff like that. So that's how energy is translated via radiation. Those changing electrons, or if some of the molecules or atoms happen to be ionized, they can readily move. But either way, the net energy is going to be increased by this radiation hitting it. All right. So, if you're talking about an ideal gas, and specifically an ideal monatomic gas, we can calculate the total internal energy, because we learn that if it's a monatomic gas, then there's no way you have any rotation like this, or rotation like this, or vibration like this, or any of that kind of stuff. We really just have translational motion, in which case we can say that the internal energy, E internal, and this is the symbol we use for internal energy in this physics class. E internal energy for an ideal monatomic gas is in the number of atoms or molecules. In this case, it has to be atoms. In the number of atoms times 1/2 mv squared bar, which is the average kinetic energy. Okay. So with that in mind, we know that the average kinetic energy, which is equal to 1/2 mv squared bar, is also equal to 3/2 kT. So we can say that the internal energy for an ideal monatomic gas is 3/2 in kT. So that is a real expression that we can use. Of course, we can also remember that K, the Boltzmann constant, is actually defined to be R, the ideal gas constant, divided by Avogadro's number, the number of atoms or molecules in a mole. Therefore, we can also write that E internal is equal to 3 halves N times R times T because of this. Basically, 3 halves N KT is equal to 3 halves N times R over NA times T, which equals 3 halves N over NA. Now you can see that N divided by NA is just our lowercase n, and we have RT. So that's why it's also equal to 3 lowercase n RT, RT over 2. Okay. Again, both of these are ideal, oops, ideal, ideal, monatomic gas. So this, for instance, it can't be, for instance, N2 or O2 or H2. They're diatomic. Okay. It can't be water vapor. It could be, gaseous copper. It could be uh, gaseous sodium or something like that, but it just can't be a more complex molecule than just a single atom. Okay, which means
So helium, it can be helium.
it
That's
could be
perfectly normal.
helium, neon. That's about it. Yeah. All right. So that's the internal energy. And we're going to use that, and we're going to use the ideal gas law a lot to do various derivations in chapter 20. But now we're going on to the specific heat. I already gave you that equation, but I haven't written it down except to solve that previous problem. So I'm going to write it down now. The heat Q added to change an object's temperature by an amount delta T. As I said, it's directly proportional to the mass of the object. It's directly proportional to the change in temperature of the object. And then we let the constant of proportionality take into account not only the constant of proportionality, but the material properties of the substance. So in that case, we get Q is equal to MC delta T, where again, Q is positive implies heat added to the system, and negative means heat taken away. Okay. The M is the mass. The C, like I said, is the specific heat, such that its units are joules per kilogram Celsius degree. Okay. And then the delta T is T minus T0 or T final minus T initial. Either one of those are acceptable. So that's what all that is. I'm going to now write it down where I can write it a little neater, and I'll box it off. So these are equations you're allowed to use and whatnot. We can also use occasionally another form of it where basically we get Q is equal to an integral. So if, for instance, you're going over a large range of temperatures, then you'd possibly want not just the specific heat, but ideally you'd like to have the specific heat as a function of temperature. So you'd know, for instance, the specific heat of water at 0 degrees Celsius is, or excuse me, at 5 degrees Celsius or roughly 10 degrees Celsius is 1 calorie per gram Celsius degree, whereas water in the solid state is like zero point 0.5 calories per gram Celsius degree. So if you're going over a large temperature range, it might be best that you instead use Q is equal to the integral from T initial to T final of m times c of t dt. So that's another thing you could use as well. Let's try an example to see what we're meaning by this stuff. So this is example 19.2, and it says uh, heat. How heat transferred depends on specific heat. How much heat input is needed to raise the temperature of an empty 20 kilogram vat made of iron from 10 degrees Celsius to 90 degrees Celsius? And two, what if the vat is filled with 20 kilograms of water? So A, they want to know Q equals question mark if T initial is equal to, I'm going to write this as 10.0 degrees Celsius, and T final is equal to 90.0 degrees Celsius. And I'm going to say M equals 20.0 kilograms of iron or steel, whatever you want to call it. And I'll tell you, they have a table, table 19.1, and that says that iron or steel has a specific heat of zero point 0.1. So C for iron is equal to 0.11. And you can write this as calories. This is a lowercase calorie per gram Celsius degree. Or you can write it as 0.11 kilocalories per kilogram Celsius degree. Notice I increased the numerator and the denominator by a factor of 1,000. That's why the number didn't change. Of course, we could also use it in joules from this table. And in joules, the specific heat of copper, or excuse me, of iron is 450, and that's joules per kilogram Celsius degree. You can see if
That's the
you
one I was looking for because I we did a ton of these and that one came up a lot in Chem 111.
so you did use the joule as opposed to the calorie one.
Yes, we did.
Gotcha. Okay, that's cool. Well, we have a table for it, and they sort of just expect you to do that from when you're solving physics problems in this class. So just know that it's my responsibility to give you the specific heat, but I do think it's perfectly reasonable for us to expect you guys to know the specific heat of water because it's literally defined in terms of it. So liquid water at 15 degrees Celsius has a specific heat of 1.00 calories per gram Celsius degree. All right, so first off, we wanted to know how much heat was required, and then part B, Q, if that is filled with water, and the specific heat of water is, of course, 1.00 calories per gram Celsius degree at 15.0 degrees Celsius roughly. But you could also say it is equal to 4,186 joules per kilogram Celsius degree. So let's start working this. Q is equal to MC delta T. In this case, we're going to say the mass of the iron is 20 kilograms. The specific heat of iron is 0.11 kcals per kilogram Celsius degree times 90.0 degrees Celsius minus 10.0 degrees Celsius. So I'll take that, say 20 times 0.11 times 80, and that gives me 176, which is one extra sig fig, 176 kilocalories. So that's how much heat it takes in calories. Of course, we can go ahead and convert that to joules by 1 kilocalorie. Oops. Is equal to 4.186 kilojoules. And that gives me roughly 737 kilojoules. Any questions on that?
Nope.
Yeah, that's pretty straightforward stuff, right?
Yeah, there's an entire chapter of this, and if just this over and over and over again for different metals mostly.
Exactly.
We had to do it for wood of all things in in Chem 111. So,
Gotcha. All right, now what we're doing is not only are we heating up the vat, which is made of iron, we're going to have the vat filled up with water and we want that to be increased as well. We know the iron's not going to change, so we can just keep these figures right here, right now. But what we need to figure out now is what about if we actually put 20 kilograms of water in the vat? How much would that take? So in that case, I'm saying Q, and I'll just subscript it water so we'll know that it's just for the water part. That's also equal to MC delta T. All of a sudden, my pencil started writing really. Oh, that's why. Probably this. Okay. In this case, we're going to go 20 kilograms again for water. I'm going to go ahead and use joules this time, even though I prefer to use calories because the number's so much better there. But it's 4.186 calories per joule Celsius degree, or actually 4,186 joules per kilogram Celsius degree. Now, again, this is going to go from 10 degrees Celsius to 90 degrees Celsius. So we're going to do 80 times 4186 times 20, and that gives me 6.70 times 10 to the 1, 2, 3, 4, 5, 6 joules. So total would be 70, actually 736. So 737 is roughly what it rounds to. 737 times 10 to the third plus 6.70 times 10 to the third gives me 7.43 times 10 to the fifth joules. Why did that get 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 740 times
I
10 to the
assume on
6th?
homework and tests it'll specify whether it wants calories or joules.
Yes, usually they're multiple choice, but sometimes they're in addition to that, not necessarily multiple choice. But yeah, they'll give you the answer that you have to have, unless it's not multiple choice, in which case it doesn't matter unless I explicitly tell you. So that should make some sense. There you go. It's supposed to be 7.4 times 10 to the 6. I don't know why the 5 came in there. Something happened. So, any questions on that one, Shannon?
No, this is again, this is
Pretty remedial stuff, right?
oh, not only did I do it in Chem 111 and the ideal gas laws in Chem 112,
Hmm.
and no, I'm doing cell biology this semester, and I was literally doing calories last night
Gotcha.
for that class. So like If there's one thing that's been hammered to death, it's this section.
Gotcha. Well, that'll be helpful. Sometimes students need a little break in their scary physics class.
Yes.
Conceptual example 19.3 says a very hot frying pan. It says you accidentally make a bad mistake by letting an empty iron frying pan get very hot on the 200 degree Celsius stove. What happens when you dunk it into a few inches of cool water in the bottom of the sink?
It
Well, the fi
cracks. It
yeah.
cracks is what happens.
Will the final temperature be midway between the initial temperatures of the water in the pan? Will the water start boiling? Assume the mass of the water is roughly the same as the mass of the frying pan. This is where they're trying to point out that water is such a great insulator. If it wasn't such a pain to try to keep it from leaking and stuff, it would be a wonderful insulator to put inside of walls. But it also happens to be, even a 4 inch thick wall, if it's 8 foot deep, it takes just as big a dam to hold back that 4 inch wide wall 8 foot deep as it would a 8 foot deep pond that's 12 acres across. So
Don't
it's
I
really
know it?
problematic.
We had considered getting a like 110-gallon fish tank.
Yes, yeah, big difference, right?
Going from a 55 to a 110 is the
Exorbitant,
glass is way,
way
and you have to
thicker.
worry about leaks way more, and you have to have like, you functionally have to have a cock kit,
Gotcha.
a fish safe cock kit, because of the risk of leaks
Wow.
with that thing.
Well, just to give you an idea, the iron that we did a second ago, 450 joules per kilogram Celsius degree, whereas liquid water was 4,000. So it's literally like 10 times more insulative than metal. So when you're talking about taking an iron frying pan and throwing it into an equal amount of water, you're basically going to get only 1/10 of the way from the temperature that the water originally was to the temperature that the pan was. And no, the water can't boil. However, if you do take single drops and throw them on a really hot skillet or frying pan, it will actually beat up and skedaddle across the surface in a nearly frictionless way, and that's called the Leidenfrost effect. Leiden, I think it's Leidenfrost effect. We use that, for instance, when we handle liquid nitrogen, which generally people don't want you
Yeah.
to handle, but because of its extremely low temperature and the extremely high temperature of our hand, the hand actually boils the liquid nitrogen
Yes,
away and keeps a little cushion of air under it.
my high school chemistry teacher used the entire school's science budget that year to replace the whole chemical cabinet and do his liquid nitrogen ice cream. But in that, he promised he would do demonstrations for the whole school with it, with the extra liquid nitrogen. And he showed the whole, so I've seen it up close because my class was the one sort of
Gotcha.
handling the bench for him.
Yep.
But he also, and you will appreciate this, shot a wine cork through the ceiling.
There you go.
It is lodged
In the
80% of the
ceiling
way into a ceiling tile permanently because nobody else was going to climb up there and get it down.
fan. Well, that sounds like a
He just
perfectly
kind
good plan.
he kind of looked up, went oops, and then kept going.
Well, let's go ahead and get started on example 19.4. This one is one that you often do when you're dealing with drinks like tea and Pepsi and stuff like that. A lot of times it's not necessarily always warranted, but as a first order approximation, you can assume the drink is a liquid, and specifically liquid water, because that's going to be the lion's share of it. And to be honest with you, until you get it, really sweet, like a really sweet tea, the amount of tea that you actually put in the water doesn't really affect the specific heat of the water very much. But once you start putting a lot of sugar in it, it can actually change it significantly. But still, as a first order approximation, you can assume that a lot of different drinks are just going to be acting like water. So in this case, it says the cup cools the tea, excuse me. If 200 cubic centimeters of tea at 95 degrees Celsius, so this is V equals 200 cubic centimeters, which is also milliliters. Uh, if 200 cubic centimeters of tea at 95 degrees Celsius is poured into a M glass 150.0 gram glass cup initially at 25 degrees Celsius. What will be the final temperature T of the tea and cup when equilibrium is reached, assuming no heat flows to the surrounding? So we basically are pouring 200 cubic centimeters of water because it's going to act like water. We know the density of water is 1 gram per cubic centimeter, so we can automatically say this is going to be 200 grams of water at 95 degrees Celsius. And we're going to put that in contact with 150 grams of glass at 25 degrees Celsius, and we want to find out what the equilibrium temperature is. There's two ways you can do this. One of the ways we do is the following. I don't like this. I don't like this way that much, so I usually do a different way, but it's delta Q is equal to 0 is what we're supposed to do for pediatrics. Pediatrics, sorry, I just read my phone call from someone. Uh, Delta Q equals 0 is what we were supposed to do with something we call calorimetry. So we imagine putting this in a sealed container. That sealed container that doesn't lose any heat is called a calorimeter. So this calculation is called a calorimeter. The other way is the way I like. I say Q lost is equal to Q gained. That's the way I normally do calorimetry problems. But when you're doing Q lost equals Q gained, you have to make sure all the terms are positive. So the idea of always saying delta T is final minus initial, in this case, if you're using Q loss equals Q gain, you do big number minus small number. So let's work this out. I'm going to say Q lost is the heat lost by the actual T. We know that the density of water is approximately equal to the density of T, and it's equal to 1 gram per cubic centimeter. That means the mass of the T is 200.0 grams. Okay.
Please tell me we are not going to have a coffee cup calorimetry lab on this.
No, we actually have a calorimetry
Oh,
lab on
thank God. Sorry, we had
it.
so many of those and they all sucked.
Yeah, you can get decent results, but you're always going to have at least, 5 or 10% error or something. But in this case, Q lost is going to be MC delta T, and that's the mass of the T, which is 200.0 grams, times the specific heat of water, which in this case would be around the 95, but we're going to assume it's roughly the same anyways. That's 1.00 calories per gram Celsius degree times, in this case, we're going to do 95 degrees Celsius minus 25 degrees Celsius, like that. And that's going to give us, oh, no, sorry. I just forgot what I was doing. The final temperature on this, we're not going to know because we're going to set this Q loss equal to Q gain. And the final temperature for the water is actually going to be lower. So I'm going to say 95.0. Just, I really hate how this thing does this. This program just automatically jumps to an eraser at various points in time, and I have no idea why. But 95 degrees Celsius minus T would be what the Q lost is. The Q gained is the mass of the actual glass. And if I look up on the table of specific heats for glass, I see that it's 0.20. So the mass is going to be 150 grams. The specific heat is 0.20 calories per gram Celsius degree. And this one's going to have a higher final temperature. So I'm going to write T minus its initial temperature, which is 25 degrees Celsius. Now I just set them equal to each other. You're going to have 200 times 1 is 200 calories per Celsius degree times 95 degrees Celsius minus T is equal to 15 times zero point 0.2, or excuse me, 150 times zero point 0.2 would be the same thing as 15 times 2. So this is going to be 30.0 calories per Celsius degree times T minus 25 degrees Celsius like that. I can multiply the 200 times the 95, and that's going to give me 1.9 times 10 to the fourth. And actually, it's only two sig figs, so I have to stick with it that way. 1.9 times 10 to the fourth calories minus 200 reciprocal Celsius degrees times T for the for the left hand side, but for the second term, the other one's going to be 30.0 reciprocal Celsius degrees times T minus 30 times 25, and that gives me 7.5 times 10 to the 2, and that's calories. And that's all of these are lowercase calories, even though I wrote them and they look like uppercase calories. So 1.9 times 10 to the fourth is bigger than the 7.5 times 10 to the 2. So I'm going to bring those over here. Uh, so this gives me 1.97 times 10 to the fourth calories on the right hand side. That takes care of this term and this term. Now I have to pull the 200 term over to the right, and that's going to be 200 positive plus 30. So 230 times T. So now I can, oh, and this is calories on top. So that's where that works out. So now if I divide both sides by 230, I'll just get Celsius degrees. 19750 divided by 230 gives me T is equal to 85.9 degrees Celsius. I That should be enough there. Let me double check, see if the answer looks like the one they got roughly. They got 86C, so that looks pretty good. Any questions on that, Shannon?
Nope, I did three or four different labs.
Mm-hmm.
So as long
It
as I
should be
do not have to
straightforward,
set up a coffee cup this time, I'm absolutely thrilled.
right? No problem.
Because
All
those
right.
all because the other problem is they don't really make styrofoam coffee cups anymore, so the ones we have are old enough to disintegrate when you touch them.
Okay. I just want to remind you, when you do Q loss equals Q gain, all the terms are supposed to be positive. You also have to pay close attention, and this is the whole reason that I do Q gained equals Q loss. If you do the delta Q equals 0, we're going to learn that there's what we call a heat of vaporization, a heat of fusion, and that sort of thing. Those latent heats have associated with them specific signs that you got to remember. And in the heat of an exam, I often found that students, including myself, would get a little bit confused and get mixed up as to whether the sign's positive or negative. So rather than memorizing all that crap, I just did everything as Q lost equals Q gained. But if you do want to use Q summation of the Q's equals 0, then you have to keep the delta T's in the order of final minus initial, and you have to assign a sign to the latent heats as to whether it's gaining heat or losing heat in those equations. So keep that in mind.
I
I
think
think
I'll
this
use
is,
the simple version.
yeah, yeah. Do you like the Q gained equals Q lost yourself?
That makes a lot. They taught us the other version
Hmm.
in Chem 111. No, this is simpler. I'm going to do the simple version.
Yeah, it's a lot easier. You just got to keep your wits about you, figure out everything that's losing heat because, like the lab will do in class, you're going to take this object, a chunk of metal, you're going to put that in a vat of water and you're going to bring that water to a boil. The reason why you bring it to a boil is because you know at that point the temperature of the water has to be 100 degrees Celsius because it's roughly at 1 atmosphere. So when you heat that metal up, it's not easy to determine the temperature of a metal, but if you stick it in a vat of boiling water, you know it has to reach equilibrium with the water eventually, and usually quick because it's a conductor. So you know going in that the temperature of the metal is 100 degrees Celsius. Then you pull it out. Of course, you don't want to bring any of the hot water with you because that could be percent error. But then you lower it into a calorimetry cup that's made of aluminum and has water in it. Just before you throw that 100 degrees Celsius chunk of metal in it, you should check the temperature of the water in the cup. And since it's been sitting there a while, the water in the cup and the cup itself, which is made of aluminum, will have the same temperature because they're in equilibrium. Then you lower the hot metal into the bottom and you start stirring it so that it can evenly distribute the heat around. And you watch the thermometer in the calorimeter cup go up, 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 and it'll come to a stop and then start going back down. That highest temperature was the equilibrium point at which the steel had reached, the hot metal had reached equilibrium with the water and with the aluminum cup. So in that case, the thing losing the heat is just the hot object, but the thing gaining the heat is not only the water, it's the water plus the aluminum cup. So you have to have the mass of the water, the specific heat of water, you have to have the mass of the empty cup, the specific heat of the aluminum that the cup is made of, and all that, and they're both on one side. So hopefully that'll keep you straight. We only have 3 minutes left before class is over, and I know you got to rush, so we'll call it a day on that one, and you are free to go. Thanks for coming, Shannon.
Yep, I'm sorry my classes are so tight. There was only one 242 physics that fit with the only 242 chemistry they're actually running this semester.
Gotcha. I understand. It's no biggie. And luckily, I'd normally cover the same material in my online lectures, so if you ever miss anything because you have to leave early, you can always find out what it is later.
Y- Yeah, unfortunately, I can only go by the recorded videos because the online lecture is in the middle of my chemistry.
Yeah, of course. Well, have a good one, Shannon, and I will see
Yep,
you guys on Wednesday.
yep.
All right,
Bye.
take care. Bye bye. Bye.